Okay, good afternoon, people. Today, I want to discuss something on hashing tables with regards to data structures and algorithm. Now, to begin with, I would like to understand the concept of hashing. So in computer science, or basically CS, hashing table or a table map is a data structure that associates keys, that is the names, with the values or rather attributes. So now, if you look at the hashing tables, it can be compared to stuff like lookup tables, dictionaries, cache, or extended array. All these are examples of hashing tables where we associate, we link the names, which are referred to as keys, and also the values together. So now, the best example that we can actually refer to are the tables of logarithms. These tables of logarithms are best examples of hashing tables, where the number is associated with the logarithmic number. So you can see the number that you're looking for as an associated logarithmic value. So these are the best examples of hashing table, where we can see the keys and attributes put together, right? So you can see from here, okay, we can see, okay, the keys can be stuff like the names of people and the indexes, the numbers of people that we're looking for. Perhaps this can be a phone book where we can actually see hashing table, very practical, where you can see a name of someone being linked with the actual number that we're looking for, or phone number. This people is basically what you call the hashing table. So the dictionaries also are examples of hashing tables where we can see, look up a word and see the meaning of that word. So you can see there's a collection of pairs where you can see the key and the values put together. So each pair has a unique key, as we can see. So operations, okay, such as get the key, delete the key, or insert the key and the value, are the most important operations that you find in the hashing table. So just an idea, hashing table is a location of pairs, lookup functions. Hash tables are often used to implement associative arrays. Worst case time for get, insert, delete, right? Or expected time. So you can see these operations of get, insert, delete operations are the ones that are very, very important in the hashing table. Now, what is the origin of hash? Why is it called hash? So the term hash comes by the way of analog, which, okay, with standard meaning in the physical world, which means to chop or mix. So Dina wrote that Hans Peter Rand of IBM appears to have been the first to use the concept in the memo dated January 1953. The term hash came into use some 10 years later. So basically, hash comes from the word chop or mix. But we'll go for the word mix as we have seen earlier on. But the hash, okay, hashing tables, they mix the keys and the attributes or associated values. So we normally make use of hash when we're searching. So now let's look at searching versus hashing. So three methods are used. The king comparison, okay, that is the time complexity. Hashing methods such as hashing functions, expected time. Now I've got types that we use, like static hashing, and there's also dynamic hashing. Let's look at static hashing just to begin with. The word static means constant or something that is unable to grow, something unscalable. So now when you see static hashing, the idea that we're getting is we're looking at a fixed size table that we are basically considering. So a hash table that is partitioned into many buckets, and each of these lots are in odd data or records, and there's a function that can transform these keys into the address that can locate the data in the table. Then we are referring to the static hashing, okay, storing data in a fixed, right, sized table. For example, this, right? This is the bucket we're talking about, which is divided into slots like this, okay, like a crate. So now, the other extensions that we can look at in terms of hashing table is how to arrange things. So there's a top hash, and for these other sub hash or intermediate hash of slots or blocks of data. So now when we are hashing, okay, or trying to understand the hash tree, we need to understand the hash function that can be used. In addition, we have what you call one-to-many, okay, hashing function. And of course, many to one, one-to-many hashing function. Now, the one-to-one hashing function is when you refer to one particular domain, okay, and one key that is associated with that one particular area that you're looking for. For example, X on X, X on X, just like that. This is what you call one-to-one hashing method. Then you've got the other hashing method that is what you call the scheme, right? Where the tables are connected like a network. So in this case, you don't just hash only one table to get the data. You need to have a joint tables like this, and then get the data from a network of tables that are joined. This is multiple hashing as opposed to one-to-one. So what is ideal hashing? So ideal hashing uses arrays, as you can see, where each position of the array is a bucket. So a bucket can normally hold only one additional pair. What does it mean? It uses the hash function f that converts each key into the index of the range, as you can see here. So every dictionary pair with the keyword that you're looking for and the elements associated with it is stored in its own bucket. So we can see that with hashing, the block in an array, which we are calling the slot or the bucket, supposed to have a pair of things, the key and the attributes that we're looking for. So let's say, for example, this is a dictionary. If there's a word that you're looking for, then there must be that word and its meaning, right? That's called hash or mix, as the name suggests. So now what can go wrong? All right, what can go wrong with this type of arrangement? Keys that have the same home bucket are same. Okay, they're similar. For example, 22 and 26 are similar or same with respect to the what? Hash function that is in use. All right. So we expect that the bucket for 26/G is already occupied. So if these they've got same, right, same bucket, it becomes very difficult to know which attributes to go for. So that's why we need to be very careful when it comes to the bucket allocation of these data attributes. So some issues that we can actually look at. So choice of hashing function is quite tricky. So to avoid collision, that is two different pairs and the same bucket. So the size, right, or number of buckets of the hash matters. So if you have the same, right, pair in the same bucket, it's a problem, right? Which attribute are you going to go for? But if the pairs are in different buckets, it's easy to actually go for the right hashing function because you can use the keys to differentiate the buckets. Now, overflow handling method, which we are saying there is no space in the bucket for the new pair. So once you put a new pair, the buckets are not there. So this is a problem where the function will find difficult to access the data. Right. So this is an example that you're talking about here. Right. For slots, this slot 1, slot 2, and you find that some of these, okay, data buckets for similar things or similar values that are considered. So it becomes a problem in this case. Now, choice of hash function requires the following. So the requirements of the hash function, it must be easy to compute. That is to start. Complex to compute becomes a problem. And then minimum number of collisions also has to be considered, not a lot. So if your hashing function groups key values together, this is called clustering of the keys. So a good hashing function distributes the key values uniformly throughout the range. So some hash functions, that is the middle of the square, right? Return the middle digit, that is x to the power 2. Then there's division, return the modulus division, okay? And there's multiplicative, where you multiply the digits where k is a fraction. So these are some of the functions that you can use to implement the hashing in the hashing tables. It was some functions, okay, the folding, partitioning the identifier x into several parts, and add the parts together to obtain the hash address. For example, as you can see from here. So there's also what we call shift folding versus folding. And sometimes you can actually do the shift folding, right? Where you can partition, okay, a particular address or the part of the array, which can sometimes overlap. That's what we call shift. They move from one wrap to the other wrap, or one bucket of items to the other bucket of items. Then there's also what we call digital analysis. If all the keys have been known in advance, then we could delete the digits of keys having the same skewed distribution, and use the rest digit as what? Hash address. All these are the functions that can apply in the hash table. So domain is all integers. So for example, a hashing table of the size B, the number of integers that can get hashed into a bucket is basically 2 to the power 32/B. So the division method results in a uniform hash function that maps approximately the same number of keys into the bucket. So in practice, keys tend to be correlated. That's why I have to be very, very careful with the choice of the keys. Okay, so similar bias distribution of home buckets is in practice when the divisor of multiple or prime numbers of such digits. So basically what you're saying, ideally, choose large prime number for you to have multiple and correct keys that you're going to use, which will avoid collision. As you can see, this is the piece of code, okay, which is explaining what you're talking about. Okay, where int I, for I, you're using a loop to determine the size of the table, and you can actually do the hash table. Okay, this shows the number of buckets and the keys. Of course, you start by assigning to now. So what you can see is we are trying to implement the size of the hashing table and allocate it with the values that you go into the bucket. What is the criteria for hashing table? The key density or identified density of the hash table is the ratio. So loading density or loading factor of the hash table is supposed to be equivalent to this, okay, number of slots, where S is slot, B is the bucket. So overflow angle. An overflow occurs when the home bucket for the new pair, which is the key and the element, is full. So expect to be overflowing. Now, the search, searching the hash table in some systematic fashion for the bucket is not free. You can actually use this technique, linear probing or quadratic probing or random probing. So now let's look at eliminate overflows by permitting each bucket to keep a list of all pairs for which it is the home bucket. Example, using another linear list or chain. Now let's look at first of all linear probing or linear open address. So open addressing ensures that all elements are stored directly into the hash table, as it attempts to resolve collisions using various methods. So linear probing resolves the collisions by placing the data into the next open slot in the table, right? So for example, get and insert. So this is the way it's done, okay? Insert pairs whose keys are 6, 12, 34, 29, 28, 11, so on and so forth. In this case, we are going to avoid collision, whereby you actually have the same key focusing on the different attributes that can cause collision. Okay, so as you can see, you're inserting values that randomly, right? In this case, there will be no collision because there's enough space between 8 and 4, okay, between 12 and 16, there's plenty of space there. So collision is not a problem. So you can put a lot of things there. That's what you call in your copy setting. What about deleting? How do you delete? Delete 0, okay? Then this cluster for pairs, if any, to fill the vacated bucket, just like that. Right, so you start from there, delete 0, okay, you also delete on the other 4, delete on 8, delete on 12, and 16. Eventually you find that all these items will be deleted according to the pseudocode that you have looked at there. So a search cluster for pair, okay, to fill the bucket. If there is nothing, you keep on using the algorithm that you have looked at to be deleted in fashion that is known. So this is what we're talking about here. This is the code that can do that business. This is what we call linear insertion, linear probing insertion. Right. So now what are the problems of linear probing? Identifiers tend to cluster together, adjacent cluster tend to compress or increase the search time. Now there's also what we call quadratic probing, right? Linear probing searches buckets in this manner. Now, quadratic probing uses a quadratic function, the way you know it, to search, right? And there's also what you call random probing, okay, which works in operating with random numbers when searching what? When probing what? The hashing table. So there's also what you call rehearsing, all right? The sequence, if collision occurs, H1 is the hashing function. So for these functions which are there from H1 all the way to HM, and then if collision occurs, you stop this function, move to other function. That's what you call the rehashing function. There's what we call double hashing, which is one of the best methods for dealing with collision. If the slot is full, then the second hashing function is calculated and combined with the first hash function. This one. All right, as you can see, the figure here shows the chaining, how the double, okay, hashing works with chaining. This is the best example. It's the best formula for avoiding collisions. Let's compare logic. If open addressing is used, then each table slot holds at most one element, therefore the routing factor can never be greater than 1. So if external chaining is used, then each table slot can hold many elements. Therefore, the routing factor may be greater than 1. Right. So what you have just looked at here, people, we have just seen, okay, the hashing methods and also the techniques that can use to avoid collision in the hashing table. So please go through these nicely and able to understand these techniques that we looked at. See you next time, people.